In this video, I'm going to be showing you some of the geologic websites, some of my favorite websites I like to use for learning about the regional geology and my local geology for a specific area, as well as different websites that aid me and help me in my rock hounding and prospecting. So let's get right into it and start looking at these various websites. Alright, so let's look at the different geologic map websites that are available. No particular order. The first one being MacroStrat. This has a geologic map of the entire globe. R here is a mobile app. It's called Rock D. You can download it. Also has the geologic map. What is cool about it is it'll tell you the local geology based off of your current location on the home screen. And there's a lot more cool features you can use when using the app. But we're going to look at the geologic map here. And as you can see, it loads up the whole world. And you got the global geology. The thing with MacroStrat is the geology, it gives you the basic, straightforward information on the geology. So if you want to know the geology of a location quick and easily, you can get that here. Being zoomed out, like I am, it'll give you a smaller scale. So what I mean by that is you can see this purple pinkish region here. Now if I was to zoom in, it's going to give me a larger scale. See how all of a sudden all these details just popped in? So as you zoom in, it's going to give you more details on the geology the closer you're in. As I zoom out, you get less detail. So let's zoom in here to the United States. You can see a lot just popped up. And let me go to my region back at home here in Idaho and Washington. So you got all these details. So all the colors, that's going to represent each individual different layer, either a rock layer or sedimentary layer or unconsolidated deposits such as rivers and stream deposits. Those are typically shown in the yellow. So if we look at the yellow here, as you can see, it just updated once again, and you'll notice that there's these boundaries. So this is getting its information from real geologic map data, at least you'd hope so. And some maps are going to be more up to date than others. So this is just a dividing line. You also get dividing lines typically at state lines, as you can see here. But let me click here. So if I click on this unit, you'll see it pops up some information. So it gives me the name, the Palouse formation, and it gives me the associated age with these deposits, anywhere from 2.58 MA to current. You can also get some more information from this. Again, with the age, it gives you the estimated thickness of the formation. So really thin to up to 40 meters. It gives you the lithology, so siliclastic, and then it gives you the environment. And then it gives you a little bit more details, so you can read these descriptions. And if you really want to, you can click this link here and it'll give you the source where this information is being pulled from. So let's click it real quick. And apparently the file is not found. Well, that's interesting. Don't know how common that is. But let's look at this rock here. And again, this is called the Priest River Metamorphic Core Complex. And it tells you it's quartzo-feldspathic, gneisses, and schist. And then it gives you the associated age with that. And one thing I'll say right off the bat is MacroStrat gives you real quick, easy information. So let's look at this formation here. So this formation is known as the Priest River Metamorphic Core Complex and is quartzo-feldspathic gneiss and schist. You'll notice the age here, it says Precambrian, and it gives you a very wide age range. That's quite a gap in time. So that 4,000 MA, what that means is that's 4 billion. So the age for this rock is telling you 4 billion to 538 million. So that's obviously a very large time difference. Now the thing is, MacroStrat gives you quick, easy information. It'll just give you the basics. If you want more exact details, well, you'll have to go to the actual geologic publications for the actual maps, the actual published professional maps themselves, which I will show you in a moment. But if you want real quick information, real basic information about what rocks you're dealing with, the approximate ages, and a little bit of detail on it, MacroStrat is a great place to go. And it is the only map I'm showing you today that has information on a global scale. All the other maps I'll be talking about only have maps available for the United States. So let's go to Chad here. Let's see what's in Chad. I think there's some volcanic fields here. I believe this one is going to be the volcanic field. So we click on it. Oh, that's a lake. Never mind. Lake deposits. I know there's some volcanoes here in Alaska. Let's go over here to where the rift is. Here we go. We got some volcanoes. Let's click on these ones, see what we get. So it gives you the approximate age. These are quaternary volcanics. The lithology is just volcanic. So it doesn't really tell you what kind of volcanic rocks these are. Are these basalt? Are these rhyolites? It's not telling you that information. It just tells you it's simply volcanic. Let's see if this map pulls up. And it does. So it does give you the website where it's pulling these references from, and you can take a look at these references. So that's a great thing about MacroStrat, is you want to see where the information's coming from, it'll take you there most of the time. And it might have more in-depth details. It appears to have a geologic map of the entire continent of Africa. But other than that, it doesn't give you real in-depth information. These black lines, these are going to be fault lines. If you see, if I zoom in too much, it loses the geologic data completely. So I have to keep myself zoomed out a little bit to see it. So if we click on the black line, well, there's no information coming up there. What about this one? It's just telling me I'm in grasslands and woodlands. Maybe I'm zoomed in. Okay, apparently if you're zoomed in too much, it won't even pull up the information. So the lines, yeah, it just says fault. It doesn't tell me what kind of fault it is. Once again, if you want more in-depth information, we're gonna have to go to the actual published maps. So again, let me go back to the United States, and I'll pull up, let's go up to North Idaho here. You can see there's a lot going on. One thing you'll also notice, if I zoom out a little bit here in MacroStrat, you see this line? That's a fault line. If I click it, it'll tell me that it's a fault. If it loads. My internet apparently is being a little slow right now. Well, I don't know if MacroStrat is having a problem right now, or if it's just my internet not wanting to load in the information. Everything else seems fine. But one thing I was saying is, as you zoom out, you see this black line, that's a fault line, but as I zoom in, it just disappears. And I believe that's because MacroStrat is referring to all sorts of different geologic map information, and I'm not sure how it works, but I believe it starts to present different geologic map information from different data sources depending on how well you're zoomed in or out or not. So if I want to get more detailed information, I'd have to go to the actual published geologic maps. Which brings me to this next website. This is called MapView, and it is currently in beta version. It's been in beta for many years, ever since I've been using it. But on this website, this will give you the actual published professional geologic maps that have been made. And again, this is only for the United States, so if you're not in the United States, you're going to have to source out geologic maps throughout your country. But if you go to MacroStrat, you should be able to click, and it hopefully will take you to a reference page where you can view a geologic map and where that data came from. But here in MapView, you can see there's a lot going on, and it's a lot different of a setup. As we zoom in, we have Idaho, you can see the geologic map, but as I zoom in, you're going to notice, if it loads, all of a sudden it gets really messy real quick. Some maps have some coloring, some are black and white. There's all kinds of information being presented here, and what it's doing is it's overlaying all the maps. If you see my mouse here, you can come over, and it has the different map sizes. So this is the smallest scale, and when I'm talking maps, when I say small scale, you may think that would be a small map. But small scale maps are actually quite large, so these are going to be your state maps. So your small scale map, being a state map like Idaho here, it's given me the geology of the entire state of Idaho. And what that's going to do, since it's a small scale map, it's actually going to start lumping the geologic units, or that's how the people, the individuals, mapped it. This purple, I know, is the Idaho batholith. Now, the Idaho batholith, that's going to be a whole bunch of intrusive granitic rocks. Now, you could have granodiorites, there could be granites in there could be just regular diorites, there could be all sorts of different intrusive granitic type rocks that you can divide up based on the chemistry. However, in small scale maps, those might just all be clumped into one unit, and they'll just call it granitic rock or Idaho batholith. Now by clicking it, it'll pull up on the side here. You'll get some highlights, and it'll whatever's in view on your screen, it'll also pull up. So Montana's over here. That's why the Montana geologic map is showing. And then we have the Idaho geologic map, and then we also have another version of the Montana map, or at least a section of it. But let's go to the Idaho geologic map, and you'll see that this one's from 1978. Now I do know there is a newer version of this. I'm not sure why it's not popping up. Maybe if I zoom out more. There we go. Let's see. There's like a 2012 version. At least there should be. Interesting that it's not showing. Anyways, let's go to the 78 version. It'll be a perfect example of what I'm talking about with the scaling. So again, you see the purple here. That is Idaho batholith. Let's see what it labels it as. As I zoom in here to the map, you'll notice that there's all kinds of information and details. And what they have this unit labeled as is KII. So if I come over to the legend, it should tell me what KII is. Well, there's KI, there's KJI, I'm not seeing KII, but anyways, the point being, it will just say that it's Cretaceous plutons. Probably includes unmapped older and younger crystalline bodies. So it doesn't give me any more detail than that. So that's the problem with small-scale maps. They give you the general geology of the area if you just want to know the basics, but we want to know the details. And of course, it has a lot of information in the legend here, which I'll get into in a moment. Smaller maps are called larger scale because they have an incredible amount of detail, but you'll also notice how small they are. So there's 48K maps, there's 62, 100, and I typically like the 100s. It doesn't matter what you like, just know that the larger scale maps, though they are physically smaller, they're going to show you the most detail. So if I come back to the Idaho batholith here, let's go 48. We'll see if there's anything here. And there is a little bit. Let's go a little bit bigger. And this is also a great way to find maps. You'll see that there isn't maps of this size in every place. So sometimes you have to filter through to find the map you're looking for. Let's look at this one. And as you can see, it's presenting a lot more information than the smaller scale map. And as I'm looking at the Idaho batholith, you'll see there's a lot more coloration than just one color, because it's dividing more of the units of the rock based on geochemistry than just lumping it all together as plutons, because you can have lots of composition of plutons. Let's look at this map of the Sandpoint area. So if you already couldn't tell, these published professional geologic maps present way more information than the geologic maps on Macrostrat. So but on Macrostrat here you can see the geology of the Sandpoint area, but if you want the real details, you have to go to the professionally published geologic maps. And this one is from the Idaho Geologic Survey, which makes sense. We are in Idaho after all. This is an Idaho geologic map. So the first thing you should do, well, I guess it doesn't really matter what you do. You can either jump right into the map. Let's say you're interested in the geology on this point. Let's look at the point here near Sandpoint itself. So here's the town, marked and labeled. This is Lake Pend Oreille. So if you're interested in this point, you want to know what the rocks are. You might be seeing these kind of purpley rocks. This is marked as YMI. So if you want to know what YMI is, you simply just go over to the legend, look for the color and the label, YMI, and here it is. So YMI is mafic intrusive rocks, undivided, and then it gives you the age, Mesoproterozoic. So when it's a solid color, that's letting you know it's large enough where they can map it and fill it out. When it's a single line, that means it's a thin sillar dike. And you'll notice that the title here for these sections of rock is given, so these are older dikes and sills. So all of these colors are in fact dikes and sills. So YAM is amphibolite, and then we have gabbros, quartz diorite, and so on and so forth. So a good place to start if you want to know overall what's going to be in the map is to look at the legend. So you'll notice there's a lot more going on than what's in the Macrostrat map, and I personally only really look at the professional geologic maps. I might look at Macrostrat if I want to get quick information about a certain area, but if I really want to know more about a region's geology, this is where I go. So starting off with the symbols, so skinny lines with dashes, these are going to be your geologic contacts. So the contact is dashed where approximately located. So if you see where my mouse is, this is a dashed contact. So it's approximately located where this contact between YPF and YPE is located. So this is a physical contact between two units of rock. Next, we have a slightly thicker line, and this is a fault, dashed where approximately located, dotted where concealed. It is obviously noticeable that there is a fault on the map here, and you'll notice that the faults are much more bold than the contacts. You'll notice these little symbols that are also on the fault. When you see a ball like this on the end of the fault, this means that it's a normal fault. The side that has the ball indicates the direction of dip of the fault. And since this is a normal fault, this is the drop-down block. This is the block that is going down, while this side would be the block that would be going upward. We then have detachment faults, which are similar to normal faults, however, they have very shallow dips. We then have thrust faults, which are compressional in origin. So normal faults and detachment faults, those are related to extensional environments, the Earth pulling apart. Thrust faults are going to be collision, the Earth squishing together. Thrust faults also are classified with shallow dip. They're similar to detachment faults in that way, except thrust faults are coming together rather than extension. So the triangles here, this denotes also the direction of dip. So when you have the triangles or the teeth on this side of the fault, that means the dip is going this way. All right, here we have a thrust fault. So again, dashed line is approximately located, but the teeth are denoting the dip. So we have the dip going southward. And with thrust faults, the side that has the teeth is going over the top of the other side. So on this side over here, the thrust fault is thrusting over the top of this greenish unit known as YGS, because thrust faults are compressional. So this YAG, due to the fault here, would be going over the top of YGS. So YGS would end up on the bottom, while YAG would end up on the top, with the dip of the fault dipping into the ground going this direction, or this direction. So then we have also right lateral strike slip faults, noted by the arrows, or left lateral strike slip faults. And these are faults that don't really have, they can have dip, but the surface motion is side-to-side motion, similar to the San Andreas. So moving on, we then have fold axes, dotted where concealed. Arrow indicates plunge direction, so if you have a fold in your rocks, this denotes it. And with folds, we can have anticlines or synclines. Anticlines look like the shape of an A, while synclines are like an inverted A. And these are folds that occur in the rock units. Let's see if we can find some. All right, here we have an anticline noted. So the arrows are going away from each other. This means it's an anticline. So if you follow my mouse direction, if you were looking at it in cross-section, the rock would be folded in an arc. You'll also notice that there's an arrow on this end. This means it's a plunging anticline, and it's plunging in this direction, with no arrow over here. If the arrows were pointing towards each other, then it would be a syncline. Then we have a whole slew of different information. A lot of this I honestly don't look at, but the big one I do pay attention to is strike and dip of bedding, and also strike and dip of foliation. So if we zoom in here, you can see these little black lines. These are strike and dip symbols. So a geologist was out in the field and physically measured the strike and dip of these rocks. And this lets you know the direction that the rock is dipping. So these are sedimentary rocks. And due to tectonics, these can then start dipping or getting uplifted, and they can tilt. So the strike shows you the orientation of that and the dip. So this dip is pointing in this direction, so the rock is dipping towards the east at a 15-degree angle. If we come over here, the rock has a similar strike, and relative to magnetic north, that is what the strike is, while the dip is 20 degrees. A good way to picture this, the dip direction, this little knob here, is the direction that if you were to put water on it, this is the direction the water would flow downhill at a 20-degree angle. You can think of it like holding a book in your hand. You can tilt the book up at a 45-degree angle, and you can see if you were to drip water onto the book, which way it would go. That is essentially what strike and dip is showing you, except with the rock layers. And this symbol right here, when it looks like this, and it kind of looks like a T, that means the rock in this specific spot is at 90 degrees. So there is no dip because it's straight up and down. You can see here the rock is dipping eastward again at a 50-degree angle, while here it is at 65. So there's all sorts of different symbols you can read into and look up. If there's some information you don't understand, you can then look it up online based off the information in the legend and learn more about it. We then have veins, which are these red lines with these red dots, so some kind of vein, marker beds, terrace scarp. So in this particular geologic map, there was glacial activity, and they were able to measure and map any kind of glacial terrain or material left behind. So these are crests or moraines. We got the head walls of glaciers, so this would represent where the front of a glacier came to. So if there's a symbol you're not sure what it is, just go to the legend. It's pretty straightforward. So finally, let's get into the mapped units. And typically, as far as I know, every single geologic map will start off with the youngest material first, and then gradually get to the older material. So starting off, we have the youngest of the youngest, well, minus the historical man-made deposits that they have mapped by this M here. But as far as geology goes, the alluvium is the youngest material. This would be the second, the third, and so on and so forth. And then we get into the next section, glacial and flood-related deposits. And with all these materials here, we then have the Columbia River basalt group. We then have intrusive rocks. Again, solid when they're large structures, thin lines when they are too small to be mapped efficiently. We have the Priest River Complex intrusive suit, and so on and so forth. If we come to the top of the map here, it's another way of organizing all the different rock units together in the legend and dividing them up by age and correlating them. So here we have the oldest of the oldest, we have Archean rock. We have one unit of Archean rock. That is it on this whole map. For Paleoproterozoic, anything within this bar is on the map. And as you can see, we only have one Paleoproterozoic rock unit. Now for Mesoproterozoic, anything in this massive bar can be considered within that age. You'll notice that here, this unit extends into the Cretaceous. There could be a couple reasons for that. Perhaps there's similar composition rock that ended up forming in this area, both in these time periods, or perhaps the scientists are not completely sure where this rock fits on the map. Here we have the Belt Supergroup. This would be the youngest of the rock, while this would be the oldest, and they typically show it in the order of how it formed. So this is sedimentary rock, so you would start off with this layer, and then a new layer would overtop that layer, and so on and so forth, until you get an entire rock package. Then we have our intrusive rocks, which intruded during the Cretaceous. We also had some during the Eocene as well. And then the only thing in the Miocene is the Columbia River basalts that ended up flowing into here. And then all the Pleistocene and Ice Age related deposits. Now, one thing I will say before I move on is maps lie. And what I mean by maps lying is they're not perfect. A geologist, when making these maps, cannot obviously go to every little square foot on this map. That would be impossible. You'd have to spend a lifetime, not even. It would just be physically impossible to cover this whole area. So what I mean by that is, if we zoom in here, this just says YGS. But perhaps there is some kind of intrusive dike right here that didn't get mapped because no one was able to spot it. I've personally have found rock units, small rock units anyways, that were not on geologic maps. Or perhaps this contact here between these units, perhaps it's off by 100 meters. And a lot of times they'll let you know that it's approximate, like these dashed lines. But even sometimes where they're certain where the contact is, this contact can still be off by maybe 200 feet or more, depending on the map and when it was published. Sometimes, if the geologic map is old enough, units could be completely misidentified. Some older maps will have outdated information or some misidentified information. And a lot of older maps, like this one from Nevada, is in black and white, and this can make it really hard to read. You'll also notice there's no legend. This particular map, if you want to see more details, you go over to the arrow to see the next section of map. And if you keep clicking it, eventually it'll bring you to the legend. Now, just as an example, I'm not sure if this is going to be accurate, but perhaps they identified something as a basalt, like this rock here. Now, they likely got this one right. I'm just using this as an example, but other geologic maps might be more vague. They might just say basalt and not have much of a description. And then someone else comes in 20 years later, they take that rock, it may look like a basalt out in the field, But then they bring it back to the lab and realize, oh no, this isn't a basalt. According to the geochemistry, it's actually an andesite, or perhaps a dacite. Also on this website, you can view bedrock maps, surficial maps, which will only have surface geology. You can also organize by year, scale, agency, title. You can overlay or adjust the overlay of the map, so if you want it really obvious and not be able to see any of the terrain or roads below, you can do so. You can switch to the satellite view. So let's go back to the Sandpoint map. There's one more thing I want to show you. So let's say you're looking at the Sandpoint map here. You want to know more about a particular rock information. Let's say you want to know more about these intrusive rocks. Well, they tell you that they're hornblende biatites or quartz monzonites, and they're from the Cretaceous. Let's say you want to know more information. Over here, click the map. It will then bring you to this page. Sometimes it'll have PDFs that you can print off right away, or even Google Earth KMZ files. So if you want to overlay these geologic maps onto Google Earth, this is one way to do it. Unfortunately, it is not available for this map. But down here you'll see additional resources, links, and downloads. Go to Publication. In Publication, it'll bring you to yet another web page, and here it'll have the map PDF download, but also the booklet. Sometimes they'll have different names for this, but what you're looking for is the report version of the maps. It will then pull up the PDF file. And here we have the official report of the Sandpoint, Idaho, and Montana geologic map. So this will give you a load of information. You can read all about what they were talking about in mapping in this map. So it'll give you the description of the rock units. If you remember on the map here, let's go to the intrusives. It just said this was a lamperite from the Eocene. That was all. But now with the official report, it has more details. So let's go find this lamperite. So you just scroll on down, we have the intrusive rocks. You can also zoom in if you want to make the reading easier. So now it gives us a load more information on this lamperite, saying it's a biotite lamperite dike with 1 to 2 millimeter biotite phenocrysts and a fine grained ground mass. And then it even gives you a figure 8 picture to look at it, which is right here. So that is the lamperite dike, and that is what it looks like. And this is what I use, or why I use geologic maps when I'm wanting to rock hound or go prospecting. This gives me a good insight on what I'm going to be dealing with in the region. And this is how I get my information. I'm not physically going out to all these places and doing my own mapping. I mean, I do on small scale, but if I want to get an idea or an advantage of what I'm getting into, this is why I go to geologic maps and look up publications, because there's a load of information. It even tells me that there's a dike that cuts through the Sandpoint conglomerate, and it tells me it's northwest of Grouse Creek in the central north part of the map. And then it gives me an age associated with that and how they age dated it. They used argon. And then there's even a citation to another paper. So if I want to read even more information, I can. So continuing down, it then gives you a whole load of information on the different rock units. Like, look at this rock unit here. This is hornblende biotite granodiorite from the Cretaceous. Look at the information they give you just on this. You could not find this information here. It just told you what the rock was. But here, they give you all sorts of information. Now, not all of the reports are going to be this nice. A lot of them are old. A lot of them are going to be, if they do have any images at all, they're going to be in black and white. This one's relatively recent, so it has some nice color imagery. If I continue scrolling down, it should give me some geologic history, where they briefly go through all the rock units from oldest to youngest, typically to give you a geologic story for this mapped area. They might even include some more simplified geologic maps, like this is really simplified and really grouped together. They're just letting you know that pretty much relatively everything over here is belt supergroup. That YM is essentially belt supergroup, except it's been metamorphosed. And then anything that's red, XAB, this is basement rock. And then of course the associated faults for that particular map. And here is where they begin the geologic story of the mapped area. So you can read all about this. You can read the Cretaceous thrust faults, you can read on the Eocene extensional faults, and then they might even have information on individual faults such as the East Newport fault or the Purcell Trench fault, which produced some earthquakes back in 2015 that I actually was able to feel. I was in them. I believe the largest one was a 3.9. And then of course at the very bottom it gives you all kinds of different references that they used for this information, and you can then look up these references and read more on the papers. So for the best information, I highly recommend using MapView. Unfortunately, it's only for the United States, so if you're outside of the United States, you're going to have to use MacroStrat, and then hopefully it'll give you a good reference where you can find more information on the area that you're interested in that is not in the United States. But overall, if you are in the US, MapView is the way to go. It is my favorite website for geologic maps. So, quickly moving on, I'm going to show you this map from Mineral Resources Online. So this gives you all sorts of information besides just geologic information. So again, it'll give me some geologic units. Similar to MacroStrat, it just kind of groups things together. So all of this pink, this is igneous, whoa, I clicked it, wasn't wanting to do that quite yet. So this is all igneous rock. It's not telling me what it is, it's kind of lumping everything together. I know, because I've looked at geologic maps and I'm familiar with this region, that these are going to be your Columbia River flood basalts. These basalts are 16 million years old, roughly. Now, when you come into the Snake River Plain, you're dealing with younger volcanism, anywhere from 2 to only a few thousand years old, and it's just lumped it all together as igneous rock, so you don't really get a whole lot of detail here. It can give you contact information, so these are all the unit contacts. You have Alaska Geology if you wanted to look up at Alaska. You also have some other information which I don't typically use, and you probably won't find a use for it either, but this is gravity anomalies. This can be really useful depending on what you're doing with geology, like geophysics. This is all geophysical data, so this shows you different gravity anomalies in the United States. This is another gravity anomaly, so you can see there's two different types here. This particular one being isostatic. And you can see it changes things quite a bit. You can even put both of them on at the same time, but I think it overrides each other. Gamma ray, so this is uranium. And then gamma ray thorium. And then gamma ray potassium. You don't have to understand what these are, there's a lot of information here. So going down, you have all kinds of geochemistry data. You might have no use for this, but if you're just curious and you're interested, this is a great source to find some information. Like if I come back to my local region here, there's all these little dots, and these are all geochemical samples. So if I click this one near Spirit Lake, for instance, it'll then pull up another tab, and it'll bring up some information. So geographical context, the county's Kootenai, state is Idaho, so on and so forth. Gives me some more information. I can then go to geology of US states. So for this particular area, it's telling me that there's Challis intrusives. There's also some nice schist and quartzite, and these are the associated ages. There's some airborne geophysical surveys, some links to those. A lot of this information I don't understand, so I wouldn't expect you to understand it either, but it's here if you want to explore it and learn. So here is the actual sample they took. It's sample, and this is its sample ID. It tells you it's an igneous rock, and they tell you the rock name is a quartz monzonite. So if you actually go to the sample here, it'll give you loads of more information, and you can actually look at the chemical analysis. And then it'll give you the unit measurement of what was in this rock. So this rock actually contains 0.52% of water that was bound in it, as well as all of these other elements. So these are major elements. These are major rock-forming elements that you would find in igneous rock. And particularly with igneous rock, the largest one by percentage is going to be silica. Basically your quartz. And you can see that this makes up 69.8% of the rock by weight. Your potassium. This is what's going to be making up your feldspars in this rock. And then of course, some lesser elements and stuff. But back to the geochemistry, you can see there's all kinds of geochemistry you can explore here. But the big thing I use this website for is for mines. So if we come up here, we have US mine features. So if I turn this on, it's going to get crazy real quick. And you'll see that all kinds of information just loaded up. And it tells you what these are. So this symbol is an adit, this would be an air shaft, so on and so forth. The legend speaks for itself. So as I zoom in here, this is known as the Silver Valley. There's a lot of mining history here, so it makes sense that it would be saturated with all kinds of different adits. So this lets me know where adits are, and I will say by experience, not every single mine is going to be mapped. There's been times where I find adits and they're not on here. So if I click on, let's say I want to know about this adit. So I click on it, it'll pull up another tab once again. Guess I'll let that load. Again, it'll give you the geographic context, but if you come down here to prospect and mine related features, it'll let you know what these are. I'm interested in the adit. So if I click on the adit, it'll then open up another tab. It'll give me a whole slew of more information. The map date is from 1957, so that is when they mapped this, and they give you the azimuth, the county, all that, and I actually haven't used this in a while. There should be a way to get some actual good information on this. So sometimes it'll actually take you to information if there's a lot of information on this mine. So let me see if I can find a major mining area. So let's go to Lucky Friday mine. This is a currently active mine that I've been into, and I have a video up on it if you want to check it out. It'll be in the upper right hand corner. Let's see if it'll give us information on this. Oh yeah, we have a slew of information that's given us here. So the major mineral deposits of the world, we're not interested in that. This gives you geochemical database of the rock, so it's all metamorphic. So these are quartzites, argillites, and so on. This is the Lucky Friday mine, as we knew, and here are the commodities of this mine. So sometimes with certain mining locations, it'll actually tell you what they were mining. So the main thing is going to be lead, this is silver, this is gold, zinc, copper, and I'm actually not familiar with these two. I probably should know this as someone who studies geology. I need to get better actually with my element names. Let's see what this takes us to. So again, it just gives you more information. Here's the commodities again. Antimony and cadmium. And it tells you the importance. So the primary means these are the two major things they're mining. Lead being the most, silver being second. But these are both primary materials that they are mining, with gold and zinc being secondary, and then of course copper and everything else is just tertiary, meaning it's there, but they're not really, that's not what they're after. It'll then tell you information on the minerals. So chalcopyrite, that is an ore, and that is an ore of copper. It doesn't tell you that here, but you can copy and paste this into Google or whatever search engine you use, and it'll pull up that information for you. Galena, that is going to be your lead ore, so that's the major lead ore. Sphalerite, that is going to be your zinc ore. And then we have all the other minerals that are being mined up here. Now, gangue material is basically waste material. So the pyrite, they're not really concerned about. Quartz definitely is not going to really be useful. However, the quartz can contain your galena and your chalcopyrite. Quartz is just a waste rock that you have to break into to maybe free up these minerals inside. And then everything else that says trace, well, it's just trace. It's there, but it's in very, very minor amounts. And then it lets you know about alteration. It says that there's bleaching. And then there's all sorts of other information here that you can look into. It tells you the host of the rock units that they're finding these materials in, such as the Rivette Formation, the St. Regis Formation, the Wallace Formation. This is all information you can look up, and a lot of these rock units are going to be mapped on geologic maps. You can just go down a massive rabbit hole reading up on all of this information. It tells you about the ore bodies, saying it's a fissure vein, that it's tabular, it's hydrothermal, it's related to faulting, that it's fault controlled. There's just loads of information that you can read up on these different mines. So finally, to wrap up this already really long video, I'm gonna just show state maps from state geologic surveys. So a lot of geologic surveys, state surveys, will have their own interactive map. So this is an interactive map of Washington from the Washington Geologic Survey. I know Idaho also has their own interactive map of their state as well, and you can probably find other state geologic maps from the state geologic surveys on the internet. They may, however, be set up quite differently. This Washington Geologic Information Portal is set up quite nicely. So here I have it checked on surface geology, we can then change the scale. So right now it's small scale, so if you remember, this is showing you a lot of information over the state. However, things are going to be lumped. So if I turn that off and I go to a larger scale, it's going to give you a lot more detail with this particular portal. If you want to see that detail, you'll have to click it, and it'll take you to the hyperlink, which then gives you a detailed geologic map of this particular spot with all the information. And this exact geologic map is going to be on that previous map view website that I showed you before. That is where this is likely being pulled from. So back to the smaller scale map, you can click here, and it may give you some information. It's not here, but you can turn on faults, and it hopefully will load up the faults. Yep, there we go. So it's not going to show you every single fault there is. It'll probably show you the most major of faults. So if you want to see, again, the best details that you can possibly get in a geologic map, you'd go to map view and find it there. So if we turn off the surface geology, there's all kinds of information on these portals. We have subsurface geology, we have landslides, and it'll give you some kind of warning message here or some information. You may have to search around for where this is actually popping up, because I'm not seeing it actually loading up here on the portal, and some of these websites may have some clunkiness to them. They may not be perfect. Oh, there it went. There we go. So here's the landslide data, if you're interested in that sort of thing. So this will show you likely areas that have experienced landslides. Yeah, so we have recent landslides, we have fans, rockfalls and scarps, all kinds of information. We have tsunamis, so right now checked as hazards area, so if you want to know where tsunami hazards are, apparently anything within this yellow area is in a tsunami hazard zone. So let's go to the west coast, and you can see pretty much all of this in Washington is going to be tsunami hazard. So here I just looked up the Idaho Geologic Survey on the web, and go to maps and publication, and look, they do have an interactive map. Not all states may or may not have their own interactive map. So let's open this interactive map, and you can see it's similar to Washington's geologic portal, it's just a different setup. So every state is probably going to have their own unique look. And we have, again, all kinds of information. We have mine information of all the Idaho mines. We have some geochemistry again. And a lot of these geochemistries are going to be the same as before, like this spot in Spear Lake. That is the exact same sample that I looked at on that previous website. We have oil and gas, which this is going to be gas, apparently. And then, of course, we have the geology tab, which pulls up all the geology. And as you can see, I'm zoomed out, so it's kind of lumping things together. As I zoom in, hopefully it gets more detailed. Or maybe not. Maybe this is just all it's going to give me. Yeah. But here I click it, it gives me a little bit of information. I can click full description, and it gives me that full description up here. So those are the top websites I like to use when it comes to geologic maps and knowing about my local and regional geology. And it can help me, and perhaps it'll help you with your rock hounding and prospecting, because I think it is important to know what kind of geology you're dealing with, specifically if you're trying to find new spots to target on your own. So if you enjoyed this type of video, I do plan to make more of these, and eventually I might go more in depth when it comes to these geologic maps and these geologic websites, and I do have some other websites that I would also love to share with you. So I hope you found this video helpful, and until next time, I'll see you all later, and you all take care.